video, we will learn about many of the atomic models that have been used throughout history to help us understand the composition of matter, and we'll learn how the model of the atom has evolved over time as new experimental evidence has emerged. The idea that matter is composed of tiny entities called atoms is not new. The first atomic theory was proposed in 400 BCE by the ancient Greek philosophers Leucippus and Democritus. They suggested that all matter is composed of tiny, indivisible particles that they called atoms, which means uncuttable, and the different properties of matter reflect the kind of atoms that make it up. However, the atomic theory of matter wasn't accepted in mainstream science until 1808, when a meteorologist named John Dalton proposed the first atomic model. Dalton was trying to understand the physical properties of gases by exploring recent research in mass laws that seemed to be true for all forms of matter. His atomic model, often referred to as the hard or solid sphere model of the atom, was able to explain these mass laws with great success. His atomic model has 4 basic assumptions. The first is that all matter consists of atoms that cannot be created or destroyed. The second is that atoms of one element cannot be converted into atoms of another element. In chemical reactions, atoms don't change from one element to another. Atoms of the original substance simply recombine to form new substances. This assumption has actually since been proven false due to research in radioactivity pioneered by Mary Skłodowska-Curie, since in radioactive processes, atoms of one element can turn into another. The third states that atoms of an element are identical and are different from atoms of any other element. So all atoms of hydrogen always have the same mass and the same properties, but hydrogen atoms and oxygen atoms are different from each other. Finally, the last assumption is that compounds result from the chemical combination of a specific ratio of atoms of different elements. For example, the compound water, or H2O, is always composed of a 2-to-1 ratio of hydrogen and oxygen, because each unit of H2O is made of 2 hydrogen atoms and 1 oxygen atom. The assumptions provided by Dalton in his atomic model were unchallenged until 1987 through experiments performed by J.J. Thomson on cathode ray tubes. A cathode ray tube is a glass tube with metal electrodes at the end. When an electric current is applied, it creates a ray that strikes the end of the tube. While J.J. Thomson was studying these cathode ray tubes, he observed that the ray bends in a magnetic field, which indicated that the ray consists of charged particles. Second, he observed that the ray bends towards the positive plate in an electric field, which indicated that the ray consists of negatively charged particles. Finally, he observed that the ray is identical for any cathode, so these particles must be found in all matter. He determined that these negatively charged particles, which he called electrons, were far lighter than the atom. This meant that the atom could not be the smallest unit of matter, so the atomic model needed to be revised. So Thomson proposed a new model of the atom, featuring the newly discovered electrons in a sea of positive charge, like the dried fruit in a plum or a bread pudding, hence the name, the plum pudding model of the atom. Based on J.J. Thomson's research, there were 2 additional atomic models proposed. In 1902, Gilbert Lewis suggested that the electrons in an atom were positioned on the corners of a cube, and in 1904, Hantao Nagaoka suggested that electrons revolved around a massive center, like the rings around Saturn. With the discovery of this new subatomic particle, the electron, scientists were interested to know more about its properties. In 1909, Robert Millikan set out to determine the charge of this new particle by watching tiny charged oil droplets fall in a special chamber. He was able to determine the charge on each drop of oil that fell. He noticed that all the charges were multiples of negative 1.6 times 10 to the minus 19 coulombs, so that must be the charge of a single electron. Amazingly, the charge of the electron that Millikan was able to measure is within 1% of the value that's measured today. Though the plum pudding model of the atom successfully incorporated the electron, it was quickly proven false by the results of experiments performed by Hans Geiger and Ernest Marsden under the guidance of Ernest Rutherford. Geiger and Marsden shot alpha particles at a very thin sheet of gold foil and measured the deflection of the alpha particles with a screen surrounding the foil that flashed when an alpha particle struck it. Since electrons are incredibly small and the alpha particles were moving very fast, they expected that all of the alpha particles would just go straight through the foil. But instead, they observed that a small fraction of the particles were deflected back the direction they came. Based on these results, in 1911, Rutherford concluded that the atom is mostly made of empty space occupied by the electrons, but there is a small and very dense positively charged nucleus in the center of the atom. He suggested that the nucleus of the atom is composed of positively charged particles that he called protons. The atomic model he proposed based on these conclusions is often called the planetary model of the atom, since the negatively charged electrons orbit the positively charged nucleus of the atom like planets orbit the sun in our solar system. Though electrons in this model aren't confined to a plane, they can move in orbits around the nucleus in 3 dimensions. The planetary or nuclear model of the atom included the newly discovered nucleus, but there were some immediate problems with it. The most obvious problem is that positively charged things are always attracted to negatively charged things. So what was keeping the negatively charged electrons orbiting the nucleus? Additionally, the planetary model suggests that the electrons in the atom should release energy in a continuous spectrum, which would create a rainbow. But when scientists looked at the spectrum produced by exciting gaseous atoms, they observed a series of lines of different colors of light, separated by black spaces. This line spectra that was produced by these excited atoms was unique for each element. To explain this, Niels Bohr proposed a new model for the atom in 1913, which is often called the electron shell or orbital model of the atom. This model features discrete energy levels that the electrons are restricted to, which correspond to fixed orbits around the nucleus. When an electron is traveling in an orbit, the total energy of the atom does not change. If the atom gains energy, the electron will jump to a higher energy orbit further from the nucleus. If energy is then lost, the electron will return to a lower energy orbit closer to the nucleus. Using this model, we can understand that the distinct lines found in the hydrogen line spectra are due to the transitions between the fixed energy orbits within the hydrogen atom. When electrons gain energy, they jump to a higher energy orbit, and they release energy when they return to a lower energy orbit. This energy that's released corresponds to a specific color on the line spectrum, so we see lines for each of the possible transitions between orbits as the electrons return to a lower energy orbit. For example, the transition from the third orbit in the hydrogen atom to the second releases energy that has a wavelength of 656 nanometers, which corresponds to the color red. And the transition from the fourth orbit to the second has a wavelength of 486 nanometers, which is light blue in color. But despite the success, there was an immediate problem with this model as well. It was unable to explain the behavior of atoms that had many electrons. In 1920, shortly after proposing the existence of the proton, Rutherford proposed that there was another subatomic particle that exists in the nucleus of the atom that was neutrally charged, which he called the neutron. He suspected this due to recent research into atoms of the same element that have different masses, which are called isotopes. But it wasn't until the 1930s that new experimental evidence emerged that could prove the existence of Rutherford's proposed particle. In 1930, Walter Bothe and Herbert Becker observed that if you bombard beryllium with alpha particles, a neutral form of non-ionizing radiation was produced. They weren't sure what this radiation might be, but they thought it could be gamma rays. In 1932, James Chadwick realized that this neutral radiation that was being created was not gamma rays, but instead a new particle that has the same mass as the proton, the neutron. This meant that the nucleus of the atom is composed of both positively charged protons and neutral neutrons. In 1924, Louis de Broglie was trying to understand why electrons had fixed energy levels. He had the idea that perhaps matter had wave-like properties. If electrons had both fixed orbits and wave-like properties, they would only have certain allowable energies, similar to the vibrations of a guitar string that's fixed at both ends. As it turned out, de Broglie was correct. Electrons and other subatomic particles do in fact have wave-like properties. In 1926, Erwin Schrödinger was able to describe the wave-like properties of matter, which founded the branch of physics called quantum mechanics. According to quantum mechanics, the electron is not simply a small particle that orbits the nucleus. Rather, it is spread out around the nucleus in all kinds of funny shapes that correspond to the electron's energy. We refer to this density of negative charge as an electron cloud. With this, we have arrived at the modern view of the atom, a nucleus that's composed of positively charged protons and neutral neutrons, surrounded by a negatively charged electron cloud. Now that we've gone through each of the atomic models, let's take a look at some example problems. How is the Plum pudding model different from the hard sphere model of the atom? A. The Plum pudding model showed electrons making up the corners of a cube. B. The Plum pudding model described electrons orbiting a central nucleus. C. The Plum pudding model included negatively charged particles known as electrons. D. The Plum pudding model included positively charged particles known as protons. Or E. The Plum pudding model showed electrons occupying different energy levels. The hard sphere model of the atom was the first atomic model. It was proposed by Dalton. In this model, the atom is the smallest division of matter. The Plum pudding model of the atom came afterwards. It was proposed by J.J. Thomson, who discovered the negatively charged electrons inside atoms. So the Plum pudding model is different from the hard sphere model of the atom because in the hard sphere model of the atom is the smallest division of matter. But in the Plum pudding model, there is a negatively charged electron, which is smaller than an atom. So let's go through our answer choices to see which of them reflects that. Answer choice A says that the Plum pudding model shows electrons making up the corners of a cube. In the Plum pudding model, the electrons are embedded in a sea of positive charge. They don't make up the corners of a cube. This is actually a reference to Lewis's cubic model of the atom. So it's not the correct answer choice. The second answer choice says that the Plum pudding model described electrons orbiting a central nucleus. The nucleus of the atom wasn't discovered until after the Plum pudding model was proposed. This answer choice is actually a reference to Rutherford's planetary model of the atom. So it's not the one we're looking for. The next answer choice says that the Plum pudding model included negatively charged particles known as electrons. This answer choice sounds like it's exactly what we're looking for. The Plum pudding model is different from the hard sphere model because it includes these negatively charged electrons. But let's go ahead and take a look at our other answer choices, just so we know why they're incorrect. The fourth answer choice says that the Plum pudding model includes positively charged particles known as protons. This answer choice is again a reference to Rutherford's planetary model of the atom, as he suggested the term proton to describe the positively charged particles that made up the nucleus. Our final answer choice says that the Plum pudding model showed electrons occupying different energy levels. This answer choice is referring to Bohr's model of the atom, where electrons occupy fixed energy orbits around the nucleus. So as we discussed before, the Plum pudding model is different from the hard sphere model of the atom because the Plum pudding model included negatively charged particles known as electrons. Let's go ahead and take a look at another example. Which diagram most closely represents Rutherford's nuclear or planetary model of the atom? Rutherford's planetary or nuclear model is based off observations from the gold foil experiment. In the planetary model, there is a positively charged nucleus in the center of the atom, and the electrons orbit the nucleus. So let's see which of the diagrams that we have most closely represents this description of the atom. In diagram A, we have electrons in orbits around the nucleus. This certainly matches what we're looking for, so let's keep this diagram in mind. In answer choice B, we have positively charged particles in a negative charge. This diagram certainly doesn't match what we're looking for. In fact, it doesn't match any model of the atom. In answer choice C, we have particles arranged on the corners of a cube. This diagram is referencing Lewis's cubic model of the atom. In answer choice D, we have electrons orbiting a central nucleus, which is what we're looking for, so let's keep this answer choice in mind as well. Our final answer choice has negatively charged particles embedded in positive charge. This certainly doesn't describe what we're looking for, but it does describe the plum pudding model of the atom. So we've eliminated the possible diagrams to represent the planetary or nuclear model of the atom down to answer choice A or answer choice D. But what's different between these two diagrams? Both of them show electrons orbiting a central nucleus. Well, the circles in diagram A are meant to represent fixed orbits for the electrons that correspond to discrete energy levels. So this diagram is actually meant to represent Bohr's model of the atom, which features fixed orbits for the electrons due to the electrons having discrete energy levels that they occupy. So answer choice A isn't what we're looking for either, which leaves us with answer choice D, which is the correct diagram to represent Rutherford's planetary or nuclear model of the atom. So now that we've learned about all the different atomic models and worked some example problems, let's conclude with the key points for this video. The first atomic model was Dalton's hard sphere model, which established the atom as the building block of matter. J.J. Thomson's plum pudding model, which features negative charges in a cloud of positive charge, added the electron. Rutherford's planetary or nuclear model of the atom added the positively charged nucleus of the atom that was discovered in the gold foil experiments. Bohr's electron shell or orbital model added discrete energy levels for electrons. James Chadwick confirmed the existence of the neutron. In the modern model of the atom, an atom is composed of a nucleus made of positively charged protons and neutral neutrons, which is surrounded by a negatively charged electron cloud.